Hello, in this lecture I answer two questions. The first question, I find out the area of this semicircle that is inside the big quarter circle A or B. The second question, I find out the area of this green shape. So we'll start with the first question. In the drawing, we have quarter circle A or B. This is a right angle, OS equals to 3 units length. We also know that RKQ equals to RQB in its length. And our task is to find out the area of this semicircle. So first of all, we define the center of this semicircle. This point is point C. So we define the touching point of the semicircle with this quarter circle. This point is point P. So point C is the center of the semicircle, point P is the point of the semicircle itself. Of course, CP is the radius of the semicircle that we define as R. Likewise, CQ is also the radius of the semicircle, is equals to R. In the next step, we join point C and S together by a straight line. Point S is the point of tendency of tangent BO with this semicircle. So point C is the center of the circle, point S is the point of the circle itself, therefore CS is the radius of this circle, of this semicircle, that is equals to R. Here we can implement rule 1, because the radius CS is equals to R, the radius CS is drawn to point S, it is the point of tendency of tangent OB with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent OB will be perpendicular to the radius SC. If OP is perpendicular to SC, it means that this angle equals to 90 degrees in its size. And this angle also equals to 90 degrees according to rule 1. In the next step, we will do a construction. That is to say, from point Q, we will draw perpendicular on OB. Again, from point Q, we will draw perpendicular on OB. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and OB. This point is point M. Those two angles are defined as one-sided interangles. The sum of those two angles is of course 180 degrees. According to rule 22, if the sum of two one-sided interangles is equal to 180 degrees, then they must be located between parallel lines. That is to say, PO is parallel to CS. So finish quickly on rule 22. According to rule 22, if the sum of two one-sided triangles is equal to 180 degrees, then they are located between parallel lines. So in the line here, line A, line B, line C cuts those two lines and those 2 points. Those triangles alpha and beta are defined as one-sided triangles. They are located between line A and line B. And according to this rule 22, if the sum of those two one-sided triangles is equal to 180 degrees, that is to say if alpha plus beta equals to 180 degrees, then they are located between parallel lines. That is to say line A is parallel to line B. So it again that those two one-sided triangles are equal to 180 degrees, and therefore they must be located between parallel lines. That is to say PO is parallel to CS. Likewise, the sum of those two one-sided triangles is equal to 180 degrees, and therefore, according to rule 22, they must be located between parallel lines. That is to say, CS is parallel to QM. Likewise, the sum of those two one-sided triangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, PO is parallel to QM. Here, PO is parallel to QM, so if you found out that those three lines PO, CS, and OM, they are parallel to each other. Each line is parallel to the other line. So those three parallel lines are connected by line segment OP and also line segment MO. And again, those three parallel lines, QM, CS, and PO are connected by the third line QP and the third line MO. And whenever you have three or more parallel lines that connected they're connected together by other two parallel lines, by other two lines that are not parallel to each other. Here, those three lines connected with, by QP and MO. Then, in this case, you can implement Taylor's theorem in the drawing. According to Taylor's theorem, the following relationship exists between the lines that are not parallel to each other and connects the three parallel lines. The following relationship exists between QP and MO that connects those three parallel lines together. The relationship is as follows: PC over CQ equals to OS over SM. And PC over CQ equals to OS over SM. Repeat again. Here, PO, CS, and QT are parallel to each other. PQ connects the fibrous line together. I said OT also connects those three parallel lines together. According to Taylor's theorem, the following relationship exists between PQ and OT. PC over CQ equals to OS over ST. So here you can implement Taylor's theorem in our drawing. According to Taylor's theorem, the following equation is true: that PC over CQ equals to OS over SM. Again, according to Taylor's theorem, the following relationship exists between PQ and OM. PC over CQ equals to OS over SM. PC is R, it is the radius of the semicircle. CQ is also R. And it is equals to OS. OS equals to 3 units in its length according to what is given as the question. Over SM. SM is the missing side, so there it is. So in total, we actually found out that R over R equals to 3 over SM. R over R is 1, so 1 equals to 3 over SM. Here we multiply this equation by SM. And finally we get that SM equals to 3 units in its length. This is the line segment SM that equals to 3 units in its length. In the next step, we will join points O and Q together by a straight line. So join points Q and O, create the right triangle QOM. Point O is the center of the quarter circle, and therefore angle AOQ, this angle, is the center angle, because the vertex of angle AOQ is located at point O, and therefore it is a center angle. Point O, that is the center of the quarter circle. Center angle AOQ subtend on RKQ. Likewise, this is center angle QOB. It subtend on chord QB. We know that according to what is given as the question, this is center angle QOB that subtend on RQB. According to what is given as the question, RKQ equals to RQB in its length. So those two center angles subtend on equal arcs, and therefore they are equal to each other in their sizes. That is to say, center angle AOB and center angle AOQ equals to center angle POQ in its size. So I repeat quickly on rule 23. According to rule 23, center angles that subtend on equal arcs are equal to each other in their sizes. So the drawing a circle. This is a triangle angle AOB that subtend on arc AB. Likewise, this is a triangle COD that subtend on arc CD. So if arc AB equals to arc CD in its length, then those two triangles must be also equal to each other in their sizes. That is to say, alpha equals to beta. So you can implement Rule 23 in our drawing because those two triangles subtend on equal arcs and therefore are equal to each other in their sizes. That is to say, triangle AOB and triangle AOQ equals to triangle QOB in its size. So if we define the size of triangle AOQ is theta, then the size of triangle QOB must be also equal to theta because they subtend on equal arcs. Theta plus theta is 90 degrees, so the angle AOB equals to 90 degrees. So 2 theta equals to 90 degrees. And therefore theta equals to 45 degrees in its size. This is again theta equals to 45 degrees in its size. So in the right triangle QOM, angle QOM equals to 45 degrees in its size. So we focus on the right triangle QOM. In the right triangle QOM, triangle is 45 degrees. Equals to QM over MO. Repeat again, in the right triangle QOM, triangle is 45 degrees equals to QM over MO. Triangle is 45 degrees is 1. So 1 equals to QM. QM is the missing side, so it is this. Over MO. MO equals to 3 plus 3, that is 6. So in total, we found out that 1 equals to QM over 6. Here we multiply this equation by 6. And finally we get that QM equals to 6 units in its length. This is the missing side QM that equals to 6 units in its length. In the next step, we will do a construction, that is to say, from point C, that is the center of this semicircle, we will go perpendicular on QM. Again, from point C, we will go perpendicular on QM. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. And we find the touching point of the perpendicular from point C and QM. This point is point L. By doing this construction, we created quadrilateral CLMS. In quadrilateral CLMS, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, so 270 degrees plus the size of this 4th cylinder. The total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore this 4th cylinder is equal to 90 degrees in its size. So inside quadrilateral CLMS we have 4 right angles, and according to rule 5, any quadrilateral that has 4 right angles must be rectangle front as square. So that's the quadrilateral CLSM as a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle CLMS, side SM equals to side CL. But SM is 3, therefore the opposite side CL must be also equal to 3 units in its length. Likewise, according to the same rule in the same rectangle CLMS, side CS must be equal to the opposite side LM, but CS is R, it is the radius of the semicircle, therefore the opposite side LM must be also equal to R units in its length. What is the length of the missing line segment QL? From the drawing, it's very easy to say that QL in total equals to QM minus LM. Again, QL equals to QM minus LM. So write it down. QL equals to QM minus LM. So QL in total equals to QM. QM is 6. According to what we already found out. Minus LM. LM is the radius, LM equals to R. So in total we actually found out that QL equals to 6 minus R units in its length. The next step are probably this right triangle CQL, this right triangle CQL in a new page, and we refer to this right triangle, the Pythagoras theorem. According to the Pythagoras theorem, in a right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the abbreviation for Pandora restaurant. So actually this is data QCL, this is the correct of the original drawing. This data QCL turned into the Pandora restaurant. QC squared, this is the square of the hypotenuse, equals to QL squared plus CL squared. So I write it down. So QC squared, that is the square of the hypotenuse, equals to QL squared plus CL squared. QC, the hypotenuse QC equals to R, therefore QC squared is R squared. And it is equals to QL squared. QL is 3, therefore QL squared is 3 squared, that is 9, plus CL squared. CL equals to 6 minus 1, therefore CL squared equals to 6 minus 1 squared. In total, we actually found out that R squared equals to 9 plus 6 minus R squared. So R squared equals to 9 plus 6 minus R squared. We'll open the brackets of this expression and get that 6 minus R squared equals to 6 squared, that is 36, plus R squared, minus 2 times 6 times R, that is minus 12R. Here we have R squared both sides of this equation, so R squared gets cancelled. After we cancel R squared on this side of the equation, we left nothing, that is to say 0. While on the other side of the equation, we have 9 plus 36, that is 45, minus 12R. So here we add 12R to this equation. And we get that 12R equals to 45. We divide this equation by 3. And finally we get that 12R over 3 is 4R equals to 45 over 3 is 15. So in total, we should found out that 4R equals to 15. Here we divide this equation by 4. And finally we get that the radius of the semicircle R is equal to 15 over 4 units in its length. Our task is to find out the area of this semicircle. Actually, there are 5 semicircles equals to the area of the circle squared, that is to say it is pi r squared over 2. And therefore, the area of our semicircle must be equal to pi over 2 times r squared. R is 15 over 4, therefore r squared is 15 over 4 squared. So do that, if you found out the semicircle equals to pi over 2 times 15 over 4 squared. So it is pi over 2 times 15 over 4 squared. 15 over 4 squared equals to 15 squared, that is 225. Over 4 squared, that is 16. So now the semicircle in total equals to 225 pi over 16 times 2, that is 32. So the area of this semicircle equals to either 225 pi over 32 square units in size, or in terms of numbers, the area of the semicircle equals to 22.09 square units in size. So, finish with the first question. The next step, I'll present you the second question. And so the second question of this lecture. Our task in the second question is to find out the area of this green shape. So in the drawing, we have the right triangle ABC. Again, ABC equals to 90 degrees in size. Side AB of triangle ABC equals to 6 units in itself. Side AC equals to 8 units in itself. The opponent BC is the missing side. Again, our task is to find out the area of this green shape. So first of all, we implement the Pythagoras theorem on this right triangle, triangle ABC. According to the Pythagoras theorem, in this right triangle ABC, BC squared, that is the square of the hypotenuse, equals to AB squared plus AC squared. And again, according to the Pythagoras theorem, in this right triangle ABC, BC squared, that is the square of the hypotenuse, equals to AB squared plus AC squared. BC is the missing side, so here it is, so it is BC squared equals to AB squared. AB 6, therefore AB squared is 6 squared, that is 36, plus BC squared. BC is 8, therefore BC squared is 8 squared, it is 64. So in total, we found out that BC squared equals to 36 plus 64, that is 100. So BC squared equals to 100. Here we take a root out of this equation and finally that the opponent BC equals to the square root of 100, that is 10. So BC equals to 10 units in its length. What is the area of this right triangle ABC? Actually, we know that the area of any triangle equals to the base of the triangle times the height over 2. We choose the base of triangle ABC is AB, so it is the base AB times the height AC over 2. And again, the area of this triangle ABC we equal to the base AB times the height AC over 2. AB equals to 6 times the height AC, AC is 8 over 2. So total area triangle is equals to 6 times 8 over 2. 6 times 8 is 48. 48 over 2 is 24. So the area triangle is equals to 24 square units in size. You can find out the area triangle ABC in a different way. We choose the base of triangle ABC as BC, so it will be equal to BC times the base BC times the height H over 2. The height H must create 90 degrees with the base BC. So if we go from point A perpendicular to BC, it will be the height. That will define the set. So the area triangle ABC from the other side equals to the base BC times the height H over 2. BC is 10. Times the height H, that is the missing variable. We find out the height H by solving this equation over 2. Now ABC equals to 10 times H over 2. But we already found out that ABC equals to 24 square units inside, so I can solve the ABC by 24. I get that 24 equals to 10 over 2 is 5. So this expression equals to 5 edge in total, so 24 equals to 5 edge. Here we divide this equation by 5. And finally get that the height to the best edge, so 5 ABC equals to 24 over 5, that is 4.8. So the edge of this line ABC is equal to 4.8 units in its length. The next step, we define the center of this semicircle. This point is point P. Likewise, we define the center of this circle. This point is point Q. We define the radius of one circle as x. And follow the fact that those two circles are identical, the radius of the other circle must be also equal to x units in its length. We define the point of tendency of tangent BC with this circle. This point is point L. We find point of tendency of tangent BC with this circle. This point is point K. We find the point of tendency of tangent AC with this circle. This point is point Z. And we find the point of tendency of tangent AB with this circle. This point is point H. In the next step, we join points P and M together by straight line. Point P is the center of the circle, point L is the point of the circle itself, therefore PL is the radius of the circle that equals to x. The radius PL is equals to x. The radius PL is 1 to point L, that is the point of tendency of tendency B with this circle. And now, order that is 1 to the point of tendency, then tangent BC will be perpendicular to the radius LP. If BC is perpendicular to LP, it means that this angle equals to 90 degrees. This angle also equals to 90 degrees, therefore for all one. We join points Q and K together by straight line. UK is the radius of the circle that equals to R. And according to 1, this circle equals to 90 degrees. And this circle also equals to 90 degrees. In the next step, we define the touching point of those two circles. This point is point M. In the next step, we will do a construction, that is to say from point M Resolve perpendicular on BC. Again, from point M, resolve perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. So we find the touching point of the perpendicular from point M and the tangent BC. This point is point S. We have those two circles touch each other externally at point M. Point M is the touching point between those two circles, so they have an external arc between them at point M. And therefore we can implement the rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects their circles together passes for their touching point. So the one here, two circles that touch each other externally at point P. Point O is the center of the circle, point M is the point of the circle itself. Wait. Point O is the center of this circle, point M is the center of this circle, and the straight line that connects their circles together is of course the straight line OM. And according to this rule 10, the straight line OM must pass for their touching point at this point P. Again, according to rule 10, the straight line OM must pass for their touching point at this point P. So we can actually implement rule 10 in our drawing. Those two circles touch each other externally at point M. The center of this circle is here at point P. The center of this circle is here at point Q. The straight line that connects the centers together is of course the straight line PQ. According to rule 10, the straight line PQ must pass through their touching point, that is point M. And the straight line PQ must pass through their touching point, that is point M. So we join points P and Q together by some line, and PQ must pass for point M. According to rule 10, of course. And because of the fact that PQ passes for point M, it means that PMQ is one straight line. If PMQ is one straight line, it means that PM plus MQ must be equal to PQ. Again, PM plus MQ must be equal to PQ. PM is the radius of this circle that is equals to X. MQ is the radius of this circle, is also equals to X. So total PQ equals to X plus X, that is 2X. PQ equals to 2X units in its length. What is the definition of line segment SM? So again, what is the definition of line segment SM? Actually, SM is a common tangent that belongs to both circles. SM is tangent to this circle, point M, and SM is tangent to this circle, the same point M. The radius PM is equals to X, the radius PM is drawn to point M, this is the point of tendency of tangent SM in this circle. And whenever radius is drawn to the point of tendency, then tangent SM will be perpendicular to the radius MP. SM is perpendicular to MP, this angle is a right angle. According to rule 1, of course. Likewise, SM is tangent to this circle at point M. So I'm not repeat on the same explanation. Therefore, according to rule 1, this circle comes from 90 degrees in its size. So for the other PLSM, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4-piece angle. In total, it must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. And therefore, this 4-piece angle must be equal to 90 degrees in its size. So in quadrilateral PLSM, we have 4 right angles, and therefore, according to rule 5, it is a right angle. Likewise, in the small quadrilateral MQKS, we have 1, 2, 3 right angles. Therefore, this 4-piece angle must be equal to 90 degrees in its size. Quadrilateral MQKS has 4 right angles, and therefore it is a right angle. 5. So, those two quadrilaterals are both right angles. What about the big quadrilateral PQKL? In quadrilateral PQKL, we have 1, 2, 3, 4 right angles, and therefore it is a right angle. So now the big quadrilateral PQLK is a right angle because it has 4 right angles. In the next step, I'll copy the big rectangle PQKL in the new page, and we'll do a construction on the new drawing. We already found out that PQ equals to 2x, so I write it down. PQ equals to 2x. So again, PQKL is a rectangle. According to what we already found out. And PQ equals to 2x. Once we know that the opposite sides of a rectangle are equal to each other. So in rectangle PQKL, PQ equals to the opposite side LK. But PQ is 2x and therefore LK must be also equal to 2x units in its length. So it is known, if you found out that LK also equals to 2x units in its length. In the next step, we already found out that the height to the base BC of triangle ABC equals to h, and h equals to 4.8 units in its length. So we go the height to the base of triangle ABC equals to 4.8 units in its length. So for point A will go perpendicular on BC, and this will be the height to the base BC of triangle ABC. The height was created perpendicular to the base, and therefore the perpendicular from point A will be the height to the base that equals to h, and equals to 4.8. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When we find the touching point of the perpendicular from point A and BC, this point is point G. And when we find the intersection point between AQ and PM, this point is point N. Now we found out that PQ equals to 2x units in its length. But with this construction, we are there the small quadrangle P and QL. So in the small quadrangle P and QL, we have 1, 2, 3 right angles, and therefore the fourth angle must be also equal to 90 degrees in its sides. Likewise, in the quadrangle NQK, so we have 2 points with the same name, so we change. No, we have this is letter G. Okay. So in the big quadrangle NGKQ, we have 1, 2, 3 angles, and the fourth angle must also equal to 90 degrees in its size. So those two quadrangles, they are both rectangles, because they have 4 right angles. QK is of course the radius of the circle that equals to x. Likewise, PL is also the radius of this circle that equals to x. So this is a rectangle. and this is also a rectangle. Let's go for the other. So in the big rectangle NGKQ, the opposite sides are equal to each other. So QK equals to X, and therefore the opposite side NG must be also equal to X units in its length. Okay. AG is the height to the base BC that equals to H, and H equals to 4.8 units in its length according to what we have already found out. So write it down. AG, that is the height to the base BC, that is equals to H according to our definition, is equal to 4.8 units in its length. In the next step, we join points A and P together by a straight line. And we join points A and Q together by a straight line. So by doing those constructions, we're going to do triangle PAQ. What is the size of this angle? Angle A and P. Actually, those two angles are defined as corresponding angles, and they are located between the parallels PQ and LK. Why PQ is parallel to LK? PQ is parallel to LK according to the rule that the opposite sides of a rectangle are parallel to each other. We already found out that PQKL is a rectangle. PQKL is a rectangle. So the opposite sides of a rectangle PQKL are parallel to each other. That is to say PQ is parallel to the opposite side LK. So those two angles are defined as corresponding angles, and they are located between the parallels PQ and LK, and therefore they must be equal to each other and their sizes. But this angle is a right angle, therefore this angle must be also equal to 90 degrees in its size. According to the rule that corresponding angles between parallels are equal to each other. Likewise, those two angles are also defined as corresponding angles, and they are located between the same parallels, PQ and okay, and therefore they are equal to each other and their sizes. But this is a right angle, therefore this angle must be a right angle. So, if you focus on triangle, the small triangle PAQ, AN is the height to the base PQ. Again, in triangle PAQ, AN is the height to the base PQ. What is the length of AN? AN equals to AG, that is 4.8, minus GN, that is X. So in total, AN equals to 4.8 minus X. So, it again on the explanation. AN, this is 970 AN, or the height AN, is equals to AG minus NG. So AN equals to AG. AG is the height of the base BC, that is equals to N, and N equals to 4.8 minus NG. NG we just like now found out that ng equals to x. So in total, an equals to 4.8 once x units in its length. An equals to 4.8 once x units in its length. We already found out that PQ equals to the base PQ or target APQ equals to 2x units in its length. The I to the base AN equals to 4.8 once x. So there target A, the small target APQ must be equal to the base PQ, that is 2x, times the I to AN, that is 4.8 once x. So write it down, we should found out that we have the small target APQ in total. Is equal to the base PQ times the ITN over 2. And again, they have this small target APQ in total. It is equal to the base PQ times the ITN over 2. As I already mentioned before, PQ equals to 2x, and equals to 4.8 minus x, divided by 2. You have 2 in the denominator, 2 in the denominator, so 2 will get cancelled. And we're left only with x times 4.8 minus x. Here we'll open the brackets of this expression and get that 4.8x x minus x is minus x squared. So in total, if you found out the derivative of the small target APQ is equal to 4.8x minus x squared, so it's in its size. Thereafter, APQ equals to 4.8x minus x squared, so it's in its size. In the next step, we'll join points P and B together by a straight line. We'll define the point of tangency of tangent AB with this circle. This point is point F. And we join points P and F together by a straight line. PF is of course the radius of the circle is equals to x. Point F is the point of tendency of tangent AB with this circle, and therefore, according to rule 1, This angle equals to 90 degrees in its size. And this angle also equals to 90 degrees in its size. The next step, we join points Q and C together by straight line. And define the point of tendency of tangent AC with this again. This point is point Y. And we join points Q and Y together by straight line. QY is of course the radius of this circle. It equals to X. Again, point Y is the point of tendency of tangent AC in this circle, and therefore formula for 1. This angle equals to 90 degrees inside, and this angle also equals to 90 degrees. So, by doing all those constructions, we divided triangle ABC into 6 parts. This is the first part of triangle ABC, that is actually the small triangle APB. This is the second part of triangle ABC, that is actually the small triangle AQC. This is the third part of triangle ABC, that is actually the right triangle PBL. This is the fourth part of triangle ABC. This is actually the right triangle QKC. This is the fifth part of triangle ABC, that is actually rectangle PLKQ. And this is the sixth part of triangle ABC, that is actually the small triangle APQ. It is very clear that the area of triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. Therefore, the triangle ABC must be equal to the 6 shapes that I already showed you. The area of triangle ABC must be equal to the 6 shapes that I presented to you. Okay? So, the area of triangle ABC must be equal to the area of the first shape, that is actually this triangle APB, plus the area of the second shape, the triangle ABC consists of, this is actually triangle AQC, plus the area of the third shape that triangle ABC consists of, this is actually the right triangle PBL, plus the area of the fifth shape triangle ABC consists of, this is actually the right triangle QKC, plus the area of the fifth shape that triangle ABC consists of, this is actually rectangle, the area of rectangle PQKL. Plus there are the 6 shapes that triangle ABC consists of, this is actually triangle APQ. So repeat again. Now triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. That is to say, the triangle ABC plus the triangle AQC plus the triangle PPL plus the of the triangle QKC plus the triangle PQKL plus the of triangle APQ. So calculate the area of each shape separately and then add the rest together. This will be equal to the area of triangle ABC. This is equal to 24 squares in size. Area of triangle ABC equals to 24 squares in size equal to the area of triangle ABP. What is the area of the triangle ABP? The area of triangle ABP is equal to the base AB times the height of the base FP over 2. AB 6, FP is X over 2. So in total, the area of triangle ABP equals to 6X over 2. This is the first shape the triangle ABC consists of. Plus the second shape, the area of triangle AQC. The area of triangle AQC equals to the base AC times the height YQ over 2. AC is 8, AQ is X over 2. So in total, the area of triangle ACQ equals to 8X over 2. Plus the area of the third shape the triangle AC consists of. The area of this triangle PBL. The area of the triangle PBL equals to the base BL times the height LP over 2. So it is BL times LP. LP is X. So total the area of triangle BLP must be equal to BL times X over 2. Plus the area of the fourth shape that consists of the area of the triangle QKC. The area of the triangle QKC equals to the base KC times the height KQ over 2. So it is KC times KQ, this is X over 2. So it is in total equals to KC times X over 2. Plus the area of the fifth shape the triangle ABC consists of. This triangle PQKL. The area of an rectangle equals to the length of the rectangle times the width. The length PQ is 2x, the width PL is X, so total it is 2x times X. Plus the area of the sixth shape the triangle ABC consists of the referent area of this triangle APQ. So we found out that the area of triangle APQ is total equals to 4.8x times X squared. Again, the area of triangle APQ equals to 4.8x times X squared in size. So we'll simplify this expression. 24, this big expression, 24 equals to 6x over 2 is 3x, plus 4x over 8x over 2 is 4x, plus we have here VLX over 2 plus KCX over 2. So here we take x over 2 as a common factor from those two expressions. So what is left of this expression after forming x over 2 as a common factor? What is left is actually BL plus this expression, what is left from this expression after we took from it x over 2 is the common factor, what is left is actually kc plus 2x times x is 2x squared, and here 4.8x plus x squared. So we continue to simplify this expression. So 24 equals to 3x plus 4x is 7x, plus here we have this expression. Our task is to express all the areas of all the shapes that triangle consists of in terms of x. And then we have one equation, one variable that is missing, that is x, and in this way we are able to solve one equation with one variable. So we have to express those two expressions BL and KC in terms of x. So what is the value of BL plus KC? Is BL plus KC. What is the value of, what is the sum of those two expressions? Actually, it is very easy to see from the domain that if you remove from BC, line segment LK, what is left is BL plus KC. Again, if you remove from side BC, line segment LK, left only BL plus KC. So BL plus KC in total equals to BC, that is 10, minus LK, that is 2x. So BL plus KC in total equals to 10 minus 2x units in itself. So it is x over 2, and BL plus KC equals to 10 minus 2x units in its length, plus 2x squared plus 4.x minus x squared. So we'll open the brackets here and again that 24 equals to 7x plus x over 2 times 10. 10 over 2 is 5, therefore this expression equals to 5x. X over 2 times minus 2x. Minus 2 over 2 is minus 1, so total we have x minus x, as x times minus x, that is minus x squared. We also have 2x squared plus 4.8x minus x squared. So 24 equals to 7x plus 5x is 12x. Minus x squared is minus 2x squared. Minus 2x squared plus 2x squared is 0. And those four expressions will get cancelled. And we left only with 4.8x, because 7x plus 5x is 12x plus 4.x. That is actually the value of this expression in total. Repeat again, I should found out that 24 equals to 12x plus 4.8x. So 24 equals to 12x plus 4.8x is 16.8x. And again, I should find out that 24 equals to 16.8x. Here we divide this equation by 16.8. And finally we get that x equals to 24 over 16.x units in its length. So the radius of the small circles is equal to 24.6.8 units in its length. Our task is to find out the area of this function. It's very clear from the drawing that the area of this function must be equal to the area of the big right triangle ABC plus the sum of the rest of those two circles. And again, the area of the function equals to the area of the big right triangle ABC plus the sum of the rest of those two circles. So write it down. The area of the right triangle the area of the green shape in total is equal to the area of this big right triangle ABC, that is equal to 24 square inches in size. Minus the sum of those two circles. They are identical and therefore they have the same areas. So it is the area of one circle times 2. The sum of those two circles is equal to the area of one circle over 2. The area of one circle is pi x squared. So the area of the two circles must be equal to 2 pi x squared. So the sum of the areas of the two circles equals to 2 pi x squared. We already found out that the area of triangle ABC equals to 24 square inches in size, and we have minus 2 pi times x squared. X equals to 24 over 16.8. And therefore x squared will be equal to 24 over 16.8 squared. So the area of the green shape in total equals to 24 minus the value of this expression. The value of this expression in total is equal to 12 point 12.823 units in its length. In total, the value of this expression equals to 12.823 units. is again, in total derivative of this expression equals to it is 12.823 square units in size, and 24 minus 12.823 is equal to 11.177 square units in size. Repeat again, if you found out that the area that we are looking for in this question, this is the area of this green shape, in total is equal to 11.177 square units in size. So we finished with the second question. In the next step, I will summarize the lecture. We'll start with the first question, of course. Our task in the first question is to find out the area of this semicircle. The semicircle is blocked by this big quarter circle AOB. Point O is the center of the quarter circle. Angle AOB is a right angle because AOB is a quarter circle. This is line 0 at OS. This is equals to 4 units in its length. In addition, we know that RKQ equals to RQB in its length. In this quarter circle AOB. Again, our task is to find out the area of this semicircle that is inscribed by the big quarter circle AOB. It is not inscribed, but it is located inside the big quarter circle AOB. So, first of all, we defined the center of this semicircle. This point is point C. We defined the touching point between the semicircle and the quarter circle. This point is point P. Point C is the center of the semicircle. Point P is the point of the semicircle itself. Therefore, CP is the radius of the semicircle. That is equals to R according to our definition. Likewise, CQ is also the radius of the semicircle. That is equals to R. Point S is the point of tendency of tangent OB with this semicircle. So we join point C and S over there by side line. Point C is the center of the semicircle. Point S is the point of the semicircle itself. Therefore, CS is the radius of the semicircle. That is equals to R according to our definition. The radius CS that is equals to R, the radius CS is drawn to point S, that is the point of tendency of tangent OB with this semicircle. And whenever your radius is drawn to the point of tendency, then tangent OB will be perpendicular to the radius SC. If OB is perpendicular to SC, it means this is angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule 1. So in the next step we did a construction, that is to say from point Q we go perpendicular on OB. Again from point Q we go perpendicular on OB. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point Q and OB. This point is point M. Those two angles are defined as one-sided corresponding angles and are located between the sum of those two one-sided triangles is 90 degrees plus 90 degrees, it is 180 degrees. And therefore, because of the fact that the sum of those two one-sided triangles is equal to 180 degrees, they must be located between parallel lines. That is to say, PO is parallel to CS. Again, PO is parallel to CS. PO is parallel to CS. Likewise, here the sum of those two one-sided triangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, CS is parallel to QM. CS is parallel to QM. Likewise, the sum of those two one-sided triangles is equal to 180 degrees, and therefore they must be located between parallel lines. That is to say, PO is parallel to QM. PO is parallel to QM. So all the three line segments PO and CS and QM, they are parallel to each other. Line segment QP connects the three parallel lines together. Likewise, line segment M also connects the three parallel lines PO, CS, and PO together. And whenever you have three or more parallel lines that are connected by the two other lines that are not parallel to each other, you can implement Tell's theorem in the drawing. According to Tell's theorem, the following relationship exists between the two lines that connects the three other parallels. That is to say, between line QP and line MO that connects those two three parallel lines with each other. The relationship is as follows: PC over CQ equals to QS over SM, and then PC over CQ equals to OS over SM. Okay. According to Tell's theorem, now we're going PC over CQ equals to OS over SM. PC is R, CQ is also R, OS is 3, SM is the missing side. So in total, we actually found out that R over R equals to 3 over SM. R over R is of course 1. So 1 equals to 3 over SM. You multiply this equation by SM and find out that SM equals to 3 units in its life. This is line segment SM. This equals to 4 units in its life. In the next step, we join points Q and O together by straight line. By doing this construction, we get the right triangle QOM. Point O is the center of the quarter circle. The vertex of angle AOQ is at point O, that is the center of the quarter circle, and therefore AOQ is the central angle. Angle AOQ subtend on arc AQ. Likewise, we have center angle QOB that subtend on arc QB. So those two center angles subtend on equal arcs. According to what is given in the question, AQ equals to QB, and therefore they must be equal to each other in their sizes. According to rule 23. So if it's written on rule 23, according to rule 23, center angles that subtend on equal arcs are equal to each other on their sides. In a circle, this is center angle AOB that subtend on arc AB. Likewise, this is center angle COD that subtend on arc CD. So if arc AB equals to arc CD in its length, that is to say, those two center angles subtend on equal arcs, then they must be equal to each other in their sides. That is to say, alpha equals to beta. So those two center angles subtend on equal arcs, and therefore they must be equal to each other in their sizes. So if the size of this center angle equals to theta, then the size of this center angle QOB must be also equal to theta, because they are equal to each other according to rule 23. So theta plus theta is equal to angle AOB, this is a right angle. Theta plus theta equals to 90 degrees, therefore theta equals to 45 degrees in its size. This is angle QOB is equals to theta, and theta equals to 45 degrees in its size. So in triangle, the right angle QOM times 45 degrees equals to QM over MO. And again, the right angle QOM times 45 degrees equals to QM over MO. Times 45 degrees is 1. Is equals to QM is the missing side, so it is over MQ. MQ in total, it is 3 plus 3, that is 6. So in total, if you remember that 1 equals to QM over 6. Here you multiply this equation by 6 and find that the missing side QM equals to 6 units in its length. This is the missing side QM, it equals to 6 units in its length. In the next step, we did a construction, that is to say, from point C, that is the center of the semicircle, we draw perpendicular on QM. Again, from point C, we draw perpendicular on QM. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point C and QM. This point is point A. By doing this construction, we created here quadrangle CLMS. In quadrangle CLMS, we have 1, 2, 3 arterials. The sum of 3 arterials is 270 degrees, so 270 degrees plus the size of this 4 facing angle. In total, it must be equal to 360 degrees according to the rule that the sum of the angles in a quadrangle is equal to 360 degrees. And therefore, this 4 facing angle must be equal to 90 degrees in its size. So inside quadrangle CLMS, we have 4 arterials, and therefore can relate to quadrangle CLMS as a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. So a rectangle, the opposite sides of a rectangle are equal to each other. So a rectangle CLMS, side CL must be equal to the opposite side SM. But CSM is 3, therefore the opposite side CL must be also equal to 3 units in its length. Likewise, according to the symbol, in the same rectangle CLMS, side CS must be equal to the opposite side LM. But CS is out, therefore the opposite side LM, the opposite side LM must be equal to 1 unit in its length. QL, let me see that side, QL equals to QM minus LM. Again, QL equals to QM minus LM. QL equals to QM minus LM. So QL equals to QM, that is 6, minus LM, that is also. In total, QL equals to 6 minus 7 in its length. In the next step, we'll come with the green iron QCL in Olympiad, and implemented the Badal's one. This iron QCL. According to the Badal's one, and in that iron, the score of the photos equals to the sum of the squares of the perpendiculars. So this is the right triangle QCL, that is according to the original drawing. According to the Badal's one, in this iron QCL, QC squared, that is the square of the hypotenuse, equals to QL squared plus CL squared. QC is out, therefore QC squared is R squared, it equals to QC squared, and it equals to QL squared. QL is 6 minus 1, therefore QL squared is 6 minus 1 squared, plus CL squared. CL is 3, therefore CL squared is 9. So in total, R squared equals to 9 plus 6 minus R squared. So r squared equals to 9. We open the brackets of this expression. 6 times r squared equals to 6 squared. That is 36 plus r squared. Minus 2 times 6 times r. That is minus 12r. So here we have r squared on both sides of the equation. So r squared will be cancelled. This side of the equation we left with nothing. That is to say 0. While on the other side of the equation, we have 93. 9 plus 36 is 45. Minus 2r equals to 0. Here we have 45 minus 12r equals to 0. Here we added 12r to the equation, and we found out that 12r equals to 45. Here we divided this equation by 3. 12r over 3 is 4r, and 45 over 3 is 15. Simple that. And we found out that 4r equals to 15. Here we divided this equation by 4, and found out that the radius r of the semicircle equals to 15 over 4. Our test is to find out the area of this semicircle. The area of this semicircle. We know that the area of a semicircle equals to the area of the circle that is pi r squared over 2. And therefore the area of our semicircle was equal to pi r squared over 2. So it is pi over 2 times r squared. R is 15 over 4, therefore r squared is 15 over 4 squared. So we have pi over 2 times r squared times 15 over 4 squared. 15 over 4 squared equals to 15 squared, that is 225, over 4 squared it is 16. So in total, we have the semicircle equals to 225 pi over 2 times 16, that is 32. So it is 225 pi over 32 square meters in size. And again, we have the semicircle, it equals to either 225 pi over 32 square meters in size. So in terms of numbers, the area of this semicircle equals to 22.09 square meters in size. So we finish to repeat on the first question. The next step, I repeat on the second solution of the second question. In the second question, our task is to find out the area of this green shape. So, in the drawing, we have the right triangle ABC. We know that side AB of triangle ABC equals to 6 units in itself, side AC equals to 8 units in itself. Inside this right triangle ABC, we have those two circles, those two identical circles. And again, our task is to find out the area of the shaded area, in this case, is the area of the green shape. The triangle ABC is the right angle because this is the right angle. So, what is the length of the hypotenuse BC? Implemented the Pythagoras theorem in this right triangle BC in order to find out the length of the hypotenuse BC. So according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, BC squared equals to AB squared plus AC squared. Right triangle BC, according to the Pythagoras theorem, BC squared, that is the square of the hypotenuse, equals to AB squared plus AC squared. BC is the missing side, so this it is, and this equals to AB squared. AB is 6, therefore AB squared is 6 squared, that is 36. plus AC squared. AC is 8, therefore AC squared is 8 squared, that is 64 in total. BC squared equals to 36 plus 64, that is 100. So BC squared equals to 100. Here we took out of this equation and I found out that the missing hypotenuse BC is equal to the square root of 100, that is 10. So the hypotenuse BC equals to 10 units in its length. What is the area of this triangle ABC? You know that the area of triangle equals to the base of the triangle times the height over 2. We choose the base as AB, and therefore the height is AC over 2. The height is AC because it's base 90 degrees with the base. This is a right angle. So the area of triangle ABC equals to the base AB times the height AC over 2. AB is 6, AC is 8 over 2. 6 times 8 is 48, 48 over 2 is 24. So we found out that the area of this big right triangle ABC is equal to 24 square units inside. 24 square units inside. In the next step, we calculated the area of this big right triangle ABC in a different way. We choose the base as BC. So the area of triangle ABC must be equal to the base BC times the height to the base over 2. The height to the base must get 90 degrees with the base BC. So the area of triangle ABC equals to the base BC times the height to the base BC that we defined as 8 over 2. And again, I should find out that the area of the triangle ABC equals to the base BC times the height to the base that we defined as edge over 2. BC is 10, edge is the missing side, so it is, so it is 10 edge over 2. 10 over 2 is 5, so in total, the area of triangle ABC that is 24 equals to 5 edge. Here we divided the equation by 5 and found out that edge equals to 24 over 5, that is 4.8 units in its length. So the height to the base BC of triangle ABC equals to 4.8 units in its length. In the next step, we define the center of this circle, this point P. We define the center of this circle, this point Q. We define the point of tendency of tangent BC with this circle, this point L. We define the point of tendency of tangent BC with this circle, this point K. Likewise, we define the point of tendency of tangent AB with this circle, this point H. And finally, we define the point of tendency of tangent AC with this circle, this point Z. Likewise, we define the radius of one circle as x, the radius of the other circle must be also equal to x because they are identical, therefore the ones are also the same for the I. In the next step, we join points P and L together by straight line. Point P is the center of the circle, point L is the point of the circle itself, therefore PL is the radius of the circle that is equal to x according to our definition. The radius PL that is equal to x, the radius PL is drawn to point L, that is the point of tendency of tangent BC with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent BC will be perpendicular to the radius LP. If BC is perpendicular to LP, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, we join points Q and K together by straight line. QK is the radius of the circle that is equals to x. And according to rule 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. In the next step, we define the touching point between those two circles, this point M. Then we did a construction that is to start from point M, that is their touching point, with no perpendicular on BC. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. What is the definition of line segment MS? MS is a common tangent that belongs to both triangles. MS belongs to the tangent to this circle, to this circle. SM is also tangent to this circle. So it is a common tangent that belongs to both circles. Tangent SM, we have the radius PM on this circle is equal to x, the radius PM is drawn to point M, that is the point of tendency of the SM with this second. And now, the radius that is drawn to the point of tendency, then tangent SM will be perpendicular to the radius MS. If SM perpendicular to MP, means that this second equals to 90 degrees according to rule 1. Likewise, the radius QM is drawn to point M, that is the point of tendency of tangent SM with this second. Therefore, according to rule 1, this second must be equal to 90 degrees in its size. So we have here, this is the small quadrangle PMSL. Inside the small quadrangle PMSL, we have 1, 2 triangles. The sum of triangles is 270 degrees, so 270 degrees plus the size of this 4 seconds. In total must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrangle is equal to 360 degrees. And therefore, this 4 seconds must be equal to 90 degrees in its size. The small quadrangle PMSL is 4 rectangles, so therefore it is a rectangle. Likewise, inside this small quadrangle MQKS, we have 1, 2 rectangles, and therefore this 4 rectangles must be equal to 90 degrees in its size, and therefore quadrangle MQSK is 4 rectangles, and therefore it is a rectangle. So those two quadrangles, they are both rectangles. What about the big quadrangle PQKL? Quadrangle PQKL is 1, 2, 3, 4 rectangles, and therefore it is a rectangle according to rule 5. Again, quadrangle PQLK is a rectangle according to rule 5. So here we have an experiment. Actually, we can immediately prove that PQ is PMQ is one straight line, because angle PMQ equals to 180 degrees in its size, and we know that any angle that is equals to 180 degrees in its size, it is defined as a straight line. Therefore, PMQ is a straight line. We have another way to prove that PMQ is one straight line. We find that those two circles touch each other externally, they have some notch between them at point 10. We can implement rule 10. We can click on rule 10. According to rule 10, if two circles touch each other externally, then the straight line that connects the centers together passes through their touching point. In the drawing, we have those two circles that touch each other externally at point P. Point O is the center of this circle, point M is the point O is the center of this circle, point M is the center of this circle, and the straight line that connects the centers together is of course the straight line OM. According to this rule 10, the straight line OM must pass for their touching point, that is point P. Again, the straight line OM must pass for point P, that is their touching point. Or OPM is one straight line. So we can implement rule 10 in our drawing. In our drawing, those two circles have some notch between them at point M. So we can implement rule 10. The center of this circle is at point P. The center of this circle is at point Q. And the straight line that connects the centers together is of course the straight line PQ. And according to rule 10, the straight line PQ must pass for their touching point, that is point M. Again, the straight line PQ must pass for their touching point, that is point M. So therefore PMQ is one straight line. Again, PMQ is one straight line. If PMQ is one straight line, it means that PQ must be equal to PM plus MQ. PM is the radius of this circle, that is equals to x. MQ is the radius of this circle, that is also equals to x. And therefore PMQ in total must be equal to x plus x, that is 2x. Okay? PMQ it is actually PQ, because it is one straight line. So PQ in total equals to x plus x, that is 2x. So we proved in two different ways that PQ is a straight line, one straight line. And therefore PQ must be equal to 2x, and we already found out that the big quadrangle PKLQ is a rectangle. So in the next step, I copied rectangle PLKQ in the new drawing, and we did a construction in the new drawing. Actually, this is rectangle PQKL that are going to the original drawing. We only found out that PQ equals to 2x. PQ equals to 2x, and one other PQKL is a rectangle. Rectangle PQKL, the opposite sides are equal to each other. So side PQ equals to the opposite side LK. But PQ is 2x, and the opposite side LK must be also equal to 2x units in its turn. So, in the next step, we draw perpendicular to the base BC. The perpendicular, it is the height of the base. It starts from the vertex A, and it is perpendicular on BC. So it is the height of the base BC that is equal to h according to our definition. And we already found out that AG is equal to h is equal to 4.8 units in itself. Again, we already found out that the height h to the base BC equals to 4.8 units in itself. So, again, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. By doing this construction, we created the small quadrangle PNGL. Inside the small quadrangle inside the small quadrangle PNGL, we have 1, 2, 3 right angles. So we found out that this is a right angle because the big quadrangle is a rectangle. All of its angles are right angles. So again, in the small quadrangle PNGL, we have 1, 2, 3 right angles. And therefore, this form is again must be equal to 90 degrees in its size. Likewise, in the bigger quadrangle NQKL, we have 1, 2, 3 right angles, and therefore, the fourth piece again must be equal to 90 degrees in its size. So, those two quadrangles, they are both rectangles. So we know that the opposite sides of a rectangle are equal to each other. So rectangle NQKG, side QK must be equal to the opposite side NG. But QK is x, the opposite side NG must be also equal to x units in its length. In the next step, we did the construction. But before that, those two angles are defined as corresponding angles, and they are located between the parallels PQ and LK. Why PQ is parallel to LK? Because in rectangle PQKL, the opposite sides are parallel to each other. That is to say PQ is parallel to LK. So those two angles are located between the two parallels PQ and LK, and therefore they must be equal to each other and their sizes. But this is a right angle, therefore this angle must be a right angle. Likewise, actually we can prove that this is a right angle according to rule 3. But this is 90 degrees, and therefore this angle must be equal to 90 degrees, but I used another method. Those two angles, and they are defined as corresponding angles, and they are located between the same parallels PQ and LK, therefore they are equal to each other and their sizes. But this is a right angle, therefore this must be also a right angle. So in the next step, we join points A and P together by a straight line, and we join points A and Q together by a straight line. But before that, AN equals to AG minus NG. Again, AG minus NG equals to AL. Again, AN equals to AG minus NG. AG is 4.8. It is the height of the base. It is to the base BC. It is 4.8 minus NG. We just found out that NG equals to x. So in total, AN equals to 4.8 minus x. AN equals to 4.8 minus x. In the next step, we join points A and P together by side line, and join points A and Q together by side line. And doing this construction, we created the small triangle APQ. In the small triangle APQ, if we choose the PQ is the base, AN will be the I to the base PQ. Why? Because it's got 90 degrees to the base PQ. Those two angles are both right angles. So it is very easy to find out. We have this one triangle APQ. The area must be equal to the base PQ, that is 2x, times the height to the base PQ, that is AN. AN is 4.8 minus x. Okay, again, if you found out that there of the small triangle APQ equals to the base PQ times the height AN over 2. PQ is 2n, and the height of the base AN equals to 4.8 minus x over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. So we have only if x times 4.8 minus x. Open the brackets of this expression, 4.8 times x we have here. X times minus x is equal to minus x squared. So in total, this expression equals to 4.8x minus x squared. Okay, again, if equals to 4.8x minus x squared. And again, the area of this triangle if equals to 4.8x minus x squared. So it's inside. In the next step, we join points P and B together by a straight line. And define the point of tendency of tangent AB with this circle. This point is point F. So PF is the radius of this circle that equals to x. F is the point of tendency of tangent AB with this circle, and therefore according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Likewise, we join points Q and C together by a straight line. We define the point of tendency of tangent AC with this circle. This point is point Y. Then we join points Q and Y together by a straight line. QY is of course the radius of this circle, is equals to x. Again, according to 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. By doing all those constructions, we divide the triangle ABC into 6 parts. This is the first part, that is triangle APB. This is the second part, that is triangle AQC. This is the third part, that is triangle PBL. This is the fourth part, that is triangle QKC. This is the fifth part, that is triangle PQKL, and this is the sixth part, that is triangle APQ. It is very clear that the triangle ABC must be equal to the sum of the areas of the 6 shapes that it consists of. So the triangle ABC in total must be equal to the area of the first shape, that is actually triangle APB. MVP plus the area of the second shape, that is triangle AQC, plus the area of the third shape, that is triangle PBL, plus the area of the fourth shape, that is triangle QKC, plus the area of the fifth shape, that is rectangle PQKL, plus the area of the sixth shape, that is triangle APQ. The area of triangle ABC is 24 according to what we already found out. So what is the area of triangle APB? What is the area of this triangle APB? The area of triangle APB equals to the base AB times the height FP over 2. AB is 6, FP is x over 2. So in total it equals to 6x over 2. So the area of the first shape is 6x over 2 plus the area of the second shape. The area of this triangle AQC. The area of triangle AQC equals to the base AC times the height YQ over 2. AC is 8, YQ is x over 2. So in total it is 8x over 2. The area of the second shape it is equals to 8x over 2, so it's in size, plus the area of the third shape, that is the third shape, that is actually the right triangle BPL. The area of this right triangle BPL equals to the base BL times the height LP over 2. So it is BL times LP, that is x over 2. So it is BL times x over 2. So the area of the third shape equals to BL times x over 2, plus the area of the fourth shape, trigonometric consists of, then actually the base kc times the height kq over 2. kq is x, so it is in total kc times x over 2. So there are the fourth shape that trigonometric consists of, it is kc times x over 2. Plus there are the fifth shape that trigonometric consists of, it is actually this rectangle pqkl. The of an rectangle equals to the length times the width. The length PQ is 2x, the width PL is, again, the length PQP is 2x, the width PL is x. So in total it is 2x times x. So they have the fifth shape equals to 2x times x. Plus they have the sixth shape, that is the area of this triangle APQ. We already found out that the area of triangle APQ equals to 4.x plus x units in its length. Again, it is 4.8 x times x squared in size. So the triangle is equals to 24, and we simplified this expression. So it is 24 equals to 6x over 2 is 3x, plus 8x over 2 is 4x. We have here BL times x over 2 times KC plus kc times x over 2. So here we took x over 2 as a common factor for out of those two expressions. X over 2 is a common factor. So what is left from this expression, from it x over 2 is a common factor, what is left is actually BL. Likewise, what is left from this expression after from it x over 2 is a common factor, what is left is actually kc. So the sum of the values of those two expressions is equals to x over 2 times BL plus kc. 2x times x is 2x squared plus 4.x plus x squared. So we continue to simplify this expression. 24 equals to 3x plus 4x is 7x. And then x over 2 times BL plus kc. We have to express BL plus kc in terms of x, because we have in this way on the other side, on this side of the equation will be expression of x only, and on the other side we have 24, and so we have one equation with one variable that we are able to solve. So we have to turn those two BL and kc to express them in terms of x. So it is BL plus kc. What is the value of BL plus kc? It is very easy to see from the domain that if you remove from BC 97LK, what is left is BL plus kc. Again, if you remove from side BC LK, this 97LK, what is left is BL plus kc. So in total, BL plus kc must be equal to BC, that is 10, minus LK, that is 2x. So in total, BL plus kc equals to 10 minus 2x units in its length. So BL plus kc equals to 10 minus 2x units in its length. So in total, the value of this expression is x over 2 times 10 minus 2x plus 2x squared plus 4.8x minus x squared. So 24 equals to 7x. We open the brackets of this expression. X over 2 times 10 is 10 over 2 is 5, so it is 5x. We have x over 2 times minus 2x. Minus 2 over minus 2 is minus 1, so it is x times minus x, this is minus x squared, plus 2x squared, plus 4.8x, minus x squared. So 24 equals to 7x plus 5x is 12x, and we have here minus x squared is minus 2x squared, and minus 2x squared plus 2x squared is 0. So those four expressions will get cancelled, and we left only with 4.x. So in total, we found out that 24 equals to 12x plus 4.x. So 12x plus 4.8, 12x plus 4.8x is equal to 16.8x. So in total, we found out that 24 equals to 16.x. Here we divided this equation by 16.8 and when we found out that x, that is the radius that we are looking for, that is the radius of the circle, is equal to 24 over 16.8 units in its length. Our task is to find out the area of this green shape. What is the area of the green shape? It's very easy to say from the drawing that the area of the green shape must be equal to the area of the big right angle ABC minus the sum of the areas of those two circles. So the area of the green shape in total equals to the area of the big right angle ABC minus the sum of the areas of the two circles. Because of the fact that those two circles are identical, they must have also the same areas. Therefore, the sum of the areas of those two circles must be equal to the area of one circle times 2. The area of one circle is pi x squared, so the area of the two circles must be equal to 2 pi x squared. So the sum of the areas of the two circles is 2 pi x squared. So in total, the area of the green shape equals to the area of the right angle ABC, this is 24, minus 2 pi x squared. X is 24 over 16.8, and the x squared is 24 over 16.x squared. So in total, 2 pi x squared equals to 24, 2 pi times 24 over 16.8, 24 over 16 squared. So we have 24, and the value of this expression in total is 12.823. 24 minus 12.823 is equal to 11.177 units in size. So if you found out that the area of this green shape, that is the area that we are looking for in this question, in total it is equal to 11.177 square units in size. Okay, thank you very much.